Hello, I am making this video because I want someone to show where I'm wrong in my thinking. Now, this is about quantum mechanics and Bell's inequality and Bell's experiment. Now, I'm not going to propose any new theories or anything. I just want to understand if I understand the experiment correctly and the assumptions around it, because there's so much baggage in quantum mechanics. It's really hard to know what's really going on. So I wrote a Twitter post, so I'm going to kind of go through this. But my understanding of Bell's theorem is that it proves that the universe is not real. And by real, I mean, it's just such a bad terminology, but by real, I mean things retain their state even when they are not measured. So if I throw a ball at the wall and I leave the room, the ball is still traveling through the air. It has a velocity property that is maintained, even though I'm not looking at it, but we'll get onto that. Versus non-real, which is interaction is the only way to determine the state of an object, which is what happens in the quantum world, which is what Bell's inequality demonstrates. Now, my understanding of the actual experiment that has been done, let's call it the Bell test, is that you take a photon and you entangle the photon by creating two child photons. And because an entanglement essentially means that there is a constraint applied between two particles. So in the case of the experiment, a photon I think is passed through a crystal which does something and creates these two child photons that conserve angular momentum. So if you know the state of one of the child photons, and you know, I don't know, let's just say energy is conserved or something, you can work out the energy of the other child photon because you know the initial energy of the parent photon. And that's what entangled means. It means that you have two particles that are correlated. So in Bell's experiment, what it demonstrates, well, with quantum mechanics, you can only know the state of the photons when you interact with them. And I'm going to use the term interact, not measure, because I think measure is ambiguous. Because in order to measure something, you have to interact with it. You have to do some kind of, you have to affect the state of the thing you're measuring in order to find out what state it's in. So in quantum mechanics, when the particles are entangled, there is a wave function that describes potential states. Only when you interact with the particle or the photon does the state of the photon resolve or collapse the wave function, and then you can know its polarity. I think is what is tested in the Bell's experiment is that the photons are polarized with some random polarizers, and then some correlation is tested at the end of the experiment between the two entangled photons, and if there's more correlation than non-correlation, then it shows that this quantum weirdness, which I'll get onto in a minute, is happening. So the part that's weird here, because initially I would have thought these two photons are correlated, so it's not strange that if you measure one, you can know the state of the other one. But I think what's being asserted with quantum mechanics is that that's only you can only say that if you think the state is determined when the entangled photon is created or when it's polarized. But in quantum mechanics, it's saying the state is only known upon measuring or upon interaction. So it seems as if you interact with one photon to determine its state, and the indeterminable state of the other photon, which could be, I think in the Nobel Prize winning experiment, it was literally like a kilometer away. you instantaneously know the state of the other one, even though presumably you haven't resolved that state. Its resolution happens upon measuring a photon on the other side of the universe because they're entangled, and that's the strange part. But what I want to tackle is first, so that's the locality part that's often talked about. So locality is, my understanding is, if you want to move from point A to point B, you have to go through continuous steps to get to point B. You can't just instantaneously move. So it's also suggested that Bell's test violates locality, which it doesn't, but I'll get onto that. I want to tackle this first point about realism, about whether you can know the state of something without interacting with it. It's often said that this is weird because the classical world doesn't work this way. And this is why I think there's a lot of semantic confusion, I guess you call it, around quantum, which is just it's just so much baggage. The classical world isn't actually real. Because you can't prove that it is. And a principle of the scientific method is you need to be able to empirically test something in order to show that it's actually. I'm going to use real is now an overloaded term, but it's axiomatic in classical mechanics that something is real. You assume that the ball always has that velocity, but the truth is you can't know until you measure it. That applies to classical mechanics just as much as quantum mechanics. So there's a semantic argument here, which is, does the ball have a state when it starts moving on the first between two interactions? You can't know the state of a ball. You can only know some uncertainty of the state based on some constraint, and you know the constraints of the system. In classical mechanics, you know the constraints so well, your predictive power is almost certain, but there's still uncertainty in the real world. So I don't think that aspect of quantum mechanics is strange. The test proves realness doesn't exist, because you can kind of just prove that logically anyway. It doesn't exist in the classical world either. And it's not weird. It's just you operate like that all of the time, really. You only can know something is in a state instantaneously when you look at it, interact with it. On the second point, regarding how almost as if the state is this is the trickiness to this, because it's lost so much in the language. So the second part of the test is saying, how does one entangled particle know the state of the other one? It's almost as if they are predetermined, or like it goes back in time or something and looks at when you measured it and blah 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 blah. It's just noise. What I don't understand specifically with the Bell's experiment is the one unifying thing when you measure these particles, interact with these particles, is you interact with them at the exact same time. Because in order for the detectors in Bell's experiment to know it's detecting the two child entangled particles, it says at time t, any interaction I get, it's assumed that those two particles are entangled because they reach the detectors at the exact same time. So that means if you had some function of the state of a particle, you're putting in the same t value. So I don't know, let's just say it takes 24 hours for them to get to the detectors. You're putting 24 hours into the function. Why? The function surely is a pure function, so you get the same result, and they're correlated, so you get a correlated result. This is the thing I don't understand. The time is the same. If these are spinning, let's take like a classical example, I suppose. If you've got a spinning ball, and you have two balls with the same rotation but in opposite directions, at time t, the direction of one ball will be the exact opposite of the other one. It's not a surprise. even though you couldn't determine it until you measured it. Now I don't know if that makes any sense to anyone, but I want to be corrected on this. I probably haven't put this forward very well, but I'm just trying to get the thoughts out. And the other question I suppose is, it's assumed that state itself is real, but I don't think that's, like I said about classical mechanics. We don't assume that in classical mechanics, and the thing that is actually real is the constraint between two properties. The property is only a. This is my woo woo thoughts, but the property of something, the energy of something, energy is like a projection of the constraints underlying the system. So I don't see why Bell's test can't have a hidden constraint. Apparently, I think it says that it can't have a hidden variable, but there can't be a hidden constraint that is determinable, resolves when you plug in a time to this function that gives you the same answer. I don't know, because the constraint is what's real. Anyway, I'm just going to upload this and probably no one's going to watch it, but it doesn't matter. Anyway, someone just rinse me in the comments. I want some, good answers, I guess.